Okay, so in this video we're going to learn how to use the method of partial fractions to perform integration on functions of the following form. So let's say we have a polynomial on top of another polynomial, and we want to find the integral of a function of that type. There are two things that we need to consider. First of all, is the polynomial on top of a lower order than the polynomial at the bottom? And by order, I simply mean the highest power of x that is involved in the polynomial. So the order is going to be n. So if the power of the maximum, if the highest power of polynomial on top is lower than that of the bottom, then we can pretty much decompose the function as follows. We can have this fraction is going to be equal to some other function on top of a function of higher order plus b of q x plus and so on and so on. So the idea is that for anything that we have on the top needs to be one order lower, than whatever we have on the bottom. And we're going to find constants here. So if this is a polynomial, we're going to have to find values of those constants that are going to allow for this sum of fractions to become exactly equal to this. Now the second condition that we need in order to perform this kind of integration is that the denominator needs to be a polynomial that we can factorize using exact numbers. So a polynomial that we can factorize would be something like x squared plus 2x plus 1. Because we know that we can factorize this as x plus 1 times x plus 1, and there are no decimal or rational numbers involved, so that's just exact numbers. That's what I mean by fractional, because we could technically find the roots of that equation using numerical approximation methods, but that would just defeat the purpose of using an analytical solution. By that logic, we could just simply use a numerical approximation to the integral, and we'll talk about that later on in future videos. But for now, we're going to focus on the cases where we can actually factorize this using exact natural numbers or integers. So let's have a look at an example just to show you how this works. So let's say that we have the following function. Let's say that we have the following function. This is going to be x plus 6 over x squared plus 2x minus 8. So the idea is we want to have two functions. So first of all, before I do this, we need to factorize the denominator. So how can we do that? Well, we know that x squared plus 2x minus x, the minus 8, should be the following. So x minus 2 times x plus 4. And this works out because we have x times x, that's x squared. We have minus 2x plus 4x, that becomes plus 2x. And then we have minus 8 because minus 2 times 4, that's minus 8. So now the idea is we're going to have two constants, a over x minus 2 plus b x plus 4. So we're going to solve this equation to find the coefficients or the constants a and b such that this sum of fractions is going to be equivalent to this. So now what we're going to do is we can multiply both sides by this denominator. So we want to get rid of denominators in the function. So this is going to lead to the following: a x plus 4, because the x minus 2 term is going to cancel out with this one. And then for b, we're going to have x minus 2, because the x plus 4 term is going to cancel out with that one. So this is the expression we end up with. So now what we're going to do is we're going to find the values of each constant individually by substituting values of x that will get rid of the other constants. So in this case, we have two constants. So let's see what values of x we can put in so that one of the constants becomes 0 whilst the other one just remains, we can solve for it. So if we choose x equals to 2, then this becomes 2 minus 2 equals 0, so b vanishes from the equation. So let's have 2 plus 6 equals to a times 2 plus 4, that's 6. such that b is just going to be 0, and thus this is going to lead to a equals to 4 over 3. So that's going to be the first value of the constant. Now we could easily substitute this back into the equation to solve for b, but what we can do is we can choose another value of x and put it into the equation to make this 0. So it is redundant whether we substitute it back in, because we want to make it 0 to solve for b. So what the value of x we can choose is x equals to minus 4. So if we put minus 4 in here, we're going to have a times minus 4 plus 4, that's 0. And we're going to have b times minus 4 minus 2, that's minus 6. So this side is 2, this side is minus 6b, which implies that b is going to be minus 1 over 3. So this is the one thing that we're going to have. Now that we have both constants, we're going to go back to this equation and we're going to plug them into this expression. And that's going to give us the following function. So we're going to end up with 4 over 3 times 1 over x minus 2 minus 1 over 3 times 1 over x plus 4. And there's a reason I have left those fractions out of these expressions, because when we integrate them, we can simply move the constants outside of the integral and just focus on the function of x that we have here. So let's see how we can integrate this. Well, this is going to be quite simple, because if we integrate this function, remember that the linearity property of the integral means that we can integrate each of the functions individually and then just add the results together. So for this case, we're going to have 4 over 3 times the integral of this function. And if you notice, this is 1 over a linear function of x. And if we remember from what we have done in the past, when we have a function like 1 over x and we integrate that, what we're going to end up with is with natural log of x. So it makes sense that for any function that is just a linear function of x in the denominator, so x to the power of 1, we're going to have that function here in the argument of natural log of x. So I'm going to reduce the size of this. This should actually become natural log of x minus 2 minus 1/3. So now the integral of this is going to be natural log of x plus 4. Not equal, sorry, that should be plus the constant c. And we can do some rearranging here. You will notice that you can pretty much combine both of them together, but because you have a constant at the front that is different, you cannot really do that in a very neat manner, so we can just leave the answer as this. Now I'm going to show you another example that hopefully will illustrate this concept a bit further, and it isn't always as simple as it seems with this one. There's a really important thing that you need to notice, and that is that whenever you're making this substitution in here, you need to make sure that whatever you have on top for the constants is actually a polynomial that is one order lower than the denominator. So what do I mean by that? Let's say we have the function f of x equals to x squared minus 2x minus 3 over x plus 2 x squared plus 1. Now we notice something about the numerator. We could easily factorize it as well, but it doesn't really matter much. What we care about is the denominator. So we know that if we expand the denominator, we're going to get x cubed. So immediately this will be a higher order polynomial than the top, so we don't need to worry too much about it. So what we need to do here, because this is already factorized, we can have a on x plus 2 plus b over x squared plus 1. But you notice something peculiar about this. Now the highest power here is 2. And notice, what is the power of the polynomial at the top? It's 0. So it doesn't match. It needs to be exactly 1 power lower than the bottom. So what we need to do is, instead of writing just a constant b, we need to write bx plus some constant c, because remember, polynomials need to go in the order, for example, ax cubed plus bx squared plus cx plus d, and we have to include all the terms in there. So this would be the case for when you have a function at the bottom that is something like x to the power 4 minus 1. So you notice, even though this function doesn't have all those other terms, you need to still write it as that, and you will need to solve for all those constants using the same method. So this is what is really important to know, is that this function here always needs to be one order lower than the bottom. So now that we have set up that, we can multiply both sides by this. So we're going to end up with x squared minus 2x minus 3 equals to a times x squared plus 1 plus bx plus c times x plus 2. So the first thing we can do is, well, what if we put x equals to minus 2 here? This whole thing, both b and c, are going to go to 0, and we can solve for a. So let's have x equals to minus 2. So x equals to minus 2 is going to give us 4 plus 4 minus 3 equals to a times 5, and that means that a is going to be equal to 1, because we're going to have 5 here on this side as well. Now the next thing we can do is we can have x equals to 0, because that way we would actually be making b 0. So let's have x equals to 0. So this is going to be minus 3 on this side. This is going to be just a, which we know is 1, so we can make that substitution here. In fact, I'm just going to make it now so we know that that's 1. So this is going to go to 0. This is 0, so that's going to leave us with plus 2x. Sorry, plus 2c. That's what we want here. And now c is going to be minus 4 and 2, which is minus 2. And then finally we can solve for b by making the substitution x equals to 1. So if we put x equals to 1, we're going to have minus 4 on this side, and now we just substitute for the values of a and c that we had. So let's have a equals to 1. Actually, I could have chosen another concept, but 1 in this case would make it easier. So we have 2 times 8, that's just 2, plus this will become 3, so that's going to be 3 times 1 times b, that's 3b. And c, we know it's minus 2, so that minus 2 is going to be carried out with that 3 as well, so that's going to be minus 6 once we multiply that. And now if we solve for b, this is going to give us b equals to 0, because we're going to have 2 on this side, 2 on that side, so 2 minus 2, that's just going to become 0 in the end. So what we're going to end up having in the end is the following function. So our function is going to become f of x equals 1 over x plus 2 minus 2 times 1 over x squared plus 1. Now if we want to integrate this function, so what we're going to do is we're going to integrate both of them individually. So we know this immediately has to be natural log of x plus 2, because this is similar to what we did in the previous example. But now what about this? We haven't learned how to integrate something like this, and certainly we cannot use integration by parts or integration by substitution, because we don't have any relation between this and the denominator. So what can we use here? Well, here is where we need to use something called an integration table. And there are a lot of integration tables that you can find online and in books. So I suggest that you look at them, and quite often you can find expressions for integrals of functions like this. So if you remember some of the videos we did on inverse, the differentiation of inverse functions and implicit differentiation, you might remember that this is actually the derivative of the function arctan of x. We actually did a little bit on that derivation, and you know that this should be the this should be the derivative of arc tan. So this is going to become minus 2 arc tan of x plus c. So this is what the integral is going to be. So partial fractions is a very powerful method, and it works for when we have expressions like this. But you might be thinking, well, I don't really see expressions like this popping out very often. I mean, it's not a very practical function that you can use. But there is something that is very, very important, and it is when you work with differential equations. And this is something that I cover in another playlist. There is something called the Laplace Transform, which essentially is an integral that transforms a function of one variable into a different variable. And usually you get an expression, no matter what function it is. It could be a trigonometric function, an exponential function, or even some mixed function. You usually end up with a function of another variable that is something like this. It has a numerator and a denominator, and both of them are polynomials. So when you want to actually go back, when you want to invert that function to get the solution to your differential equation, you actually have to perform this method and use partial fractions to get it. So this is why this method is so important. So if you want to find out more about the applications of this, I suggest you look through my differential equations playlist, and there is a few videos that where I discuss the Laplace transform and its applications. And we actually make use of this method for solving for those problems. But for now, I'm going to conclude integration methods there, and in the next video we're going to cover something called definite integration.